Okay, so efficiency is an important idea. Okay, it hasn't always been a really big consideration, but okay, it is now. In our kind of modern society, we're really concerned with making things more efficient. Okay, so as to be more responsible with the energy we use. Okay, and of course the byproducts of that same energy. So efficiency then has to do with how much of the energy that's put into something actually ends up doing the work we want. The closer that number is to 100%, the better. The problem is most of the things we do are highly inefficient. Okay? They do not convert energy effectively from one form to another. And every time we convert energy from one form to another, energy is lost. So the more conversions of energy there are between our initial source of energy and our final work, the less efficient that process is going to be. Okay? The more times I have to convert one form of energy to another before I get to my end result, the less efficient I will be. So one way to increase efficiency is to eliminate a lot of the middle conversions. Okay? The more directly we can convert initial energy to final energy, the better. Okay? And then, obviously, the more efficient we can make that conversion, the better as well. Okay? So if we're looking at how we typically generate electricity in Alberta, okay, despite what you may be wanting to believe or what people will tell you, okay, the wind farms in Pincher Creek do not provide a huge amount of power to the power grid in Alberta. It's less than 5%. Okay? The bulk of our electrical energy in Alberta is provided by what? Oil and gas. And coal. Okay? Less coal now, but it was typically a lot of coal. Okay? And that's not necessarily a bad thing. Our coal-fired plants are very efficient and they're, well, somewhat efficient, they're very clean. Okay? Yes, they put a lot of carbon dioxide out, but that's the nature of combustion. Okay? But they don't put out a lot of soot and particulates and things like that. But the problem with using fossil fuels of any kind to produce electricity is there are a lot of conversions from the initial source of energy to electricity. Okay? What's the initial source of energy for a fossil fuel? Chemical. Okay. And the only way to release chemical energy is to do what? Turn it into heat. Okay? Chemical energy is potential energy. It doesn't do work on its own. And the only thing you can do with chemical potential energy is release it as thermal energy by burning. Okay? Now, for a typical coal-fired or natural gas-fired electrical generation plant, okay, the most important part of that plant is what we call the boiler. Okay? The boiler is basically like a gas stove pot of water. Okay? That's really all it is. When it comes right down to it, that's what it is. A big burner and a big pot of water over top of it. Okay? So we're converting the energy that's in the fossil fuel into thermal energy, which is then warming water. What does the water have to do? It has to turn into steam. It has to evaporate. Okay? Now, is energy going to be lost between the burner and the boiler? Yeah, no matter how much you try and contain that process, energy is going to be lost. Okay? And it has to be, because the thing would melt down if we actually managed to trap it all. Okay? So a lot of it just goes out the stack, okay, as wasted thermal energy. A lot of it. Okay? Now, some of it does end up converting the water into steam. Now, the steam has to move through pipes towards the what? Okay, towards the turbine. So I've taken thermal energy, I've taken chemical energy, I've converted it into thermal energy. That thermal energy is converting or changing the state of water so that it has more thermal kinetic energy. Okay? And then that thermal kinetic energy is turned into kinetic mechanical energy as it travels through a pipe and turns the turbine. Okay? So in the turbine, I'm converting kinetic energy from one form to another, from the movement of the steam to the movement of the turbine. The turbine is then turning mechanical energy into electrical. Every time I convert energy from one form to another, I lose some. Okay? No matter how efficient I make a turbine, it's still going to generate heat because of friction. Okay? But yes, it's going to generate some electricity as well. Okay? Now, that process, like you see, it's not super efficient. It's not terrible either. Okay? But it's certainly not making use of 100% of the available chemical energy that was stored in the coal or gas or whatever we use. Okay? Now, the same could be true for generating electricity with a wind turbine. Okay? There's problems with that process as well. Okay? Wind has to, first off, be present. Okay? And it isn't always. Okay? I mean, Pitcher Creek is always windy, but okay, I mean, it's not the same amount of windy every day, right? So it's not as reliable a source of energy because you're depending on something you can't control. I can control the fuel supply of coal or gas to a coal-fired or gas-fired plant, but I can't control when wind happens. Okay, so there's one drawback to that. But when it is present, it's still taking kinetic energy in the wind and having to convert it into mechanical energy of the spinning turbine. Actually, the spinning fan blade, which is then connected to the turbine, okay, which is then connected to the generator. Okay, so that all has energy conversions from one form to another. Okay, it's more direct. Okay, it's more direct, which makes it more efficient. Okay? But again, it's not a source of energy we can always count. All right, the same is true for solar energy. Okay, we can't rely on solar energy here, and not as part of a power grid, especially this time of year, because we only get 6 hours of sunshine, and it's very low angle. It's not very direct, it's not very intense, it's certainly not doing very much this time of year. It's great in the summertime, when we're getting 18 hours. Okay? Now, could you use solar energy in Victoria? It's way too rainy. It's cloudy all the time. Okay? In fact, they have I think it's less than 60 days of sunshine a year. Okay. Yeah, it is depressing. It's like Seattle. Okay? It's why such great grunge and alternative stuff came out of Seattle because it's always rainy and depressing. Okay. But yeah, if you don't have a constant supply of high intensity direct sunshine, solar energy is not great for you either. Is it more efficient when it's present? Yes, because it's a much more direct conversion of the initial source of energy to the final source. Okay. But it has to be present all the time. Okay. Everyone okay with that? Okay, so if we want to increase efficiency, we have to make sure that we're putting the initial source and the final source close together. Okay, not a lot of intermediate conversions. Now, to give you some idea, something we rely on every single day, and just how inefficient it is. And I'm not trying to knock cars. Okay, and I'm not trying to knock internal combustion engines. Okay. I will go to my grave before driving an electric car. It's just, I'm just not going to drive an electric car. Okay? But are they more efficient than an internal combustion engine? Way more. Yeah. Okay? An electric car is way more efficient than an internal combustion engine because the initial source of energy and the final source of energy are much closer together. And there's a lot less heat produced by an electric motor. Okay? So the initial energy and the final energy are much closer together in terms of the string of events. Okay? In an internal combustion engine, we start with potential energy in the fuel, chemical. Okay? It has to be released as thermal energy. That thermal energy drives the pistons up and down, so the thermal energy gets converted into mechanical, which is then converted into different forms of mechanical energy about 4 times before it actually gets to the wheels. Okay? How much of that thermal energy actually gets used to drive the car? It's pretty low. Yeah, it's pretty low. A lot of it just goes right out the tailpipe. Okay? So to give you an idea here, let's say you put $100 worth of gas in your car, which at today's gas prices is hard. I know right now I'm dreading going to the gas station because my truck is near empty and I've got the extended fuel cell for towing. It's 136 liters. Okay? I'm that guy that stands there and jiggle up. Okay? Yeah, I get to stand next to the pump for 10 minutes. Okay? So the exhaust system and what's the exhaust system's job in your car? Yeah, your exhaust system's job is to vent toxic gases from the engine out the back of the car so as not to poison you. Okay? That's why if you have an exhaust leak, you need to get it fixed. People drive around with holes in their exhaust and don't realize that carbon monoxide can get into the cab of the car from a leaky exhaust system. Or if you had what happened to the bus the other day, it happened to you, there's like been this like horrible epidemic of people going out and cutting the catalytic converters off of vehicles. Okay? No, really.
They're expensive.
Because there's precious metals inside of them, and what they're doing is they're pulling them, they're just cutting them off of people's cars, and then they're selling the scrap. Okay? Yeah. If that happens, you can't keep driving your car around for a couple of reasons. There's a lot of oxygen sensors and pollution control in the catalytic converter, and your car's check engine light will come on immediately, okay? And it won't run right. But secondly, there's a big hole in your exhaust system, and the catalytic converter is usually right underneath the passenger compartment. Okay? So toxic gases are going to be getting into the passenger compartment. Okay? So if you've ever noticed, the end of your exhaust system is usually out the back and or side of the vehicle, okay? Venting away the toxic gases. And on most cars, if they have only single exhaust, it is on the passenger side, okay? Not on the driver's. Okay, so the exhaust system, whose only job is to vent heat and hot gases, takes 33%, $33 of the $100 worth of fuel in your car, and push it out the back of the car. It does not produce thrust. Okay? It does not drive the car forward. Okay?
Someone should come up with something like that.
Someone should, but it's not there. Okay? It does not produce any useful work in terms of moving the car forward. Okay? But it takes 1/3 of the energy in your fuel. Okay? 1/3 of the energy in your fuel is simply vented as hot gas out the back of the car. Okay? All right. Your cooling and heating system. Your car is so inefficient that it needs to use 1/3 of the energy in it to keep it from melting down. Okay? So in your car is something called a water pump. Okay? Sometimes you can hear these if they're broken. You ever drive by a car and it's squealing? Okay, that's a bad water pump. Okay? The pump is just, basically the belt is just screaming past and squealing like crazy. Okay? So the water pump's job is to circulate the coolant through the engine block and to the radiator. Okay, so what happens is the engine coolant goes into your engine block and absorbs heat from the engine, and then goes to your radiator, which radiates the heat out into the environment. Okay, keeping your car cool. If your coolant starts to leak and you've got a little puddle of green goo under your car, that's bad. Okay, first off, the radiator coolant is toxic. Okay, and it's very sweet. If your pets drink it, they'll die. Okay, it's actually quite dangerous. If you see a puddle of green goo under your car, you have pets, keep them away from it. Okay, but that stuff, okay, it basically has to vent away a lot of the extra heat that is produced by the combustion of fuel. Right? So we have now used 2/3 of the energy in the fuel, and we have not moved yet. Okay? This is just to keep the engine running and us alive. Okay? 2/3 of the energy in the fuel. Your drive train, okay? That is the part of the car that converts the mechanical energy of the moving pistons into rotational energy at the wheels. Okay? There is a lot of friction in those parts. And it takes 10% of the energy in your fuel just to keep that going. Okay? Your accessories. This number is probably low. For a modern car, this number is probably higher because we have a lot more accessories than we used to. You've got power door locks, windshield wipers, headlights, touch screen maybe on your car, rear window defroster, okay, your like heater, your air conditioner, okay, all of that kind of stuff. Power sunroof, whatever. Okay, you got all that electrical stuff basically in your car. Okay, that can take anywhere from 4 to 8 or even higher % of the energy in your fuel. It's all powered by something called an alternator. Okay, an alternator is a small generator that has a belt on it. Okay, that belt is attached to the main drive shaft of your car. When the drive shaft turns, okay, it pulls on that alternator, spins the alternator, generating electricity. Right? When you put on more high demand electrical items, more power is drawn away from the wheels to the alternator. Okay, so you have to be aware of that. Okay? If you're wanting to get more power, usually you have to turn some electrical things off. The air conditioner, the rear window defogger are two of the biggest electrical draws, okay, in your car. So they can take a lot of energy. If you have one of those big stereos,
I know there's somebody, I call him this guy who just like drives by my house all the time. Okay. Those can take a lot of energy, right? In fact, when I worked in Lloydminster, when I first started teaching, we had this car show. The kids would do this car show every year, and this one kid had this stereo in his like Mustang, like his 1985 Fox body Mustang, and he had to have 2 alternators. He had to install a second alternator to power all the amplifiers that he had in the car. Okay. Now, this was one of the coolest things I ever saw in terms of like engineering stupidity. But he had a bunch of subs in the hatch. This was a hatchback Fox body Mustang, and he had all these subs. Like there must have been 6 or 8 of them in the back. But you couldn't put any cargo in this thing. The back hatch was full of speakers. Okay. And he would do this thing that he called the Looney Dance. He would flip a loony onto the top of the car and then crank the stereo, and the loony would bounce with the beat. And it would just bounce along the top of the car. Okay? And then one day, he decided he was going to see as loud as it could go. He couldn't sit in the car. He had to get out. Okay? And he turned it up, and the back window spiderweb. There was so much force from the speakers that the back window just went. Okay, now this is a hatchback, so it's a big rear window with the defogger. The electrical lines, those are expensive. It was worth more than the car. Okay, like so was the stereo. Okay? He had like $8,000 worth of stereo in the car with $1,500. Okay? Yeah, but I mean, hey, you do what you want to do with your vehicle. Okay, totally worth it. And his reaction was just so funny because when it's spiderweb, my reaction was, and he was like, that's who he was. But, yeah. So those accessories, anything electrical, okay, can take energy away. The more electrical devices you have in the car, okay, the more energy it's going to take. If you got, all your friends are doing a road trip and everybody's got their phone plugged into the stuff and they're charging it, your alternator is going to draw more power. Okay. Internal friction, 6%. Okay, now, are there things you can do about this? Sure, change your oil often. Okay, use synthetic oil, things like that. Those can all reduce internal friction. Not significant, maybe 1%, maybe something like that, but it's all important. Okay, so in the end, for an average size vehicle, this is not like every vehicle, for an average size passenger car, okay, you're looking at about 14% of the energy in your fuel that actually efficiently drives the car forward. Okay, so every day you get in your car and you say, I'm okay with my car being somewhere between 10 and 20% efficient. Okay, the bigger the car, the more powerful the engine, the less efficient the car will be. Okay?
What about when you call it better fuel?
Actually, fuel isn't as important as you would think.
Oh.
Okay, most cars, they have to run a certain type of fuel. Okay, and I don't mean like gas versus diesel. Don't put the wrong fuel. Okay, that's really bad.
Put diesel in gas.
Yeah, well, if you put gas in the diesel engine, it will destroy it. Vice versa, same. Okay, but if you have a car that's supposed to run on the regular 87 octane fuel, okay, don't put mid-grade, don't put premium in it. It's not good for it. Okay, that stuff that runs hotter than the fuel it's supposed to run. They can foul up and mess up your sensors, which are expensive. Okay, it's not going to make your car necessarily run any better. Your computer in your car is set to do things with a certain level of fuel. Okay, now some cars will run on what's called E85 ethanol blended fuel. You can't get that in Canada and very many places. It's big in the States. Okay, it's a lower octane fuel and it's got a lot of alcohol in it. Okay, as opposed to like regular fuels. It's a lot cheaper, but you don't get nearly as good a gas mileage or power out of it. So there's a trade-off. Okay, but in general, you want to stick with the fuel recommended in your owner's manual. If it's supposed to run on premium, then you got to put premium in. Okay, if you have something like a more high-end vehicle and it has a turbo, okay, it'll often require premium fuel. Okay, Ford's EcoBoost would be an exception. It can run on the regular 87 octane, but most turbocharged vehicles, especially if they're high compression, will require premium fuel. Okay, and so you have to pay more for that, about 10 to 15 cents per liter. Okay, but it burns hotter. Doesn't necessarily make the car more efficient. And in fact, in a lot of cases, it's less.
Okay, so yeah, but it's faster. Okay, anything that gives the car more power makes it less efficient. Okay,
Power is good.
power's good.
Power is good.
Power's good. Okay, but it makes the car less efficient. Okay, make no mistake. If you're, just pushing your gas a little bit and accelerating slowly, you're accelerating more efficiently. It's no fun though. Okay, it's only fun when pedal meet floor. Okay, pedal meet floor, go faster. Okay, that's more fun, but it's less efficient. Okay, yeah, hearing 8 pop cans going up and down, screaming, hollering, that's awesome. Okay, but it's not efficient. Okay, and the bigger your motor, okay, the less efficient it's going to run in general, simply because there's going to be more friction. Okay, the bigger it is, the more friction there's going to be. Okay, the more heat's going to be generated, as opposed to things like that. All right. So, systems with moving parts always lose energy as heat. Okay, they have to, because as soon as parts are moving past each other, there's going to be friction. Okay, that is going to move away from the system, okay, or into the surroundings according to the second law of thermodynamics. It's the second law of thermodynamics that kind of governs how efficient something can be. Okay, so for efficiency, okay, we calculate efficiency by dividing the amount of useful work that was done, that is the job we wanted. We divide that number in joules by the amount of work actually required to do it. That is, how much energy did I put in? Okay, so how much useful work was done divided by how much work had to be done. Okay, or how much energy I had to put in. Basically, an easier way to write this would be output divided by input. Okay, and I usually write like output energy versus input energy. Okay, if I divide those two numbers, I'm going to get a decimal, okay, which represents a percent efficiency. Okay, so if I put in, let's say I have a job that in the end does, let's say 85 joules worth of useful work, but I had to put in 120 joules worth of energy to accomplish it. Okay, then my efficiency is going to be, okay, 71%. Right, but that's actually good. Okay, that's a fairly efficient process. Most of the time, we're looking at numbers that are less than 50%. In fact, when you do this calculation for your conservation of energy lab, you're going to be shocked. Okay, simply running a cart down a ramp is incredibly inefficient. Okay, you're going to get a number, probably most of you, close to 50%. Okay, for the efficiency. Yes, you would. Yeah, in any calculation. Not on your lab, because I don't know how you measure it. But yeah. Okay, so that's how we calculate efficiency. Output, or useful work, divided by input, or input work. Okay, so what you get out versus what you had to put in, that's how you calculate efficiency, and it's just a percentage. Okay? All right, so just as some examples here. Automobile internal combustion engine, 12 to 15%. They're probably a little bit better than that now. Okay, we're making engines more and more efficient all the time. Okay, you could probably get an average passenger car now that's 20. Okay, maybe even a little bit higher than that. Okay, an electric vehicle is going to be even more efficient than that. Okay, electric motors are highly efficient. The computers control their traction, so there's not slippage and things like that. Okay, so they do run at a much higher efficiency than an internal combustion engine. Okay, electrical engines can be up to 95% efficient. Okay, and the reason for that is there's not a lot of internal friction in an electrical engine. Okay, an electric motor has magnets, and the magnets repel each other, and that's how the motor spins. They're not in contact with each other, so there's very little friction except where the drive shaft is. Okay, that's why they're so incredibly efficient. Versus an internal combustion engine, which has pieces of metal sliding inside of other pieces of metal up and down. Okay, there's a lot of friction there. It's not nearly as efficient. Okay, now it probably makes it sound like I'm telling you should not have an internal combustion engine and you should have an electrical engine. Okay, I'm not saying that. Really, you have to do your homework and then you have to decide that for yourself. Okay? Everyone likes the idea of an electric car because it doesn't have the same carbon footprint as an internal combustion engine. There are two things you need to consider about that. Okay? Number one, yes, you're probably going to have a smaller carbon footprint provided the source of your electrical power is not fossil fuels. Okay? in Alberta, unless you put a bunch of solar panels on your roof and have a wind turbine up there and that's directly connected to charging your car, probably not. Okay? You're still, yes, it's more efficient, so that will be lowering your carbon footprint, but you're still in the end getting the energy from something that combustion fuel would provide. Okay? The other thing to consider is the batteries themselves. Okay? Yeah, they're lithium-ion batteries. The process of mining lithium is pretty awful. Okay? And they don't last forever. They contain toxic chemicals. They have to be disposed of at some point. Now, I'm not saying an internal combustion engine doesn't contain toxic chemicals too. It does. Okay? But those things can be drained and put away. But okay, they still have to be disposed of. Okay? So do the batteries for an electric car. Okay? We have to get those materials from somewhere. So you really have to do that research for yourself and then decide for yourself. Okay? If am I going to burn a lot of fossil fuels and put in greenhouse gases and things like that? Am I going to have electric motor that doesn't do that as much but still has toxic chemicals in it that I have to get rid of? You can't get something for nothing. Okay? At some point you're poisoning something. Okay? You just have to poison. All right. So electrical engine, like we said, up to 95% efficient. A reciprocal steam engine, okay, 50 to 75. A steam turbine engine, about 40. Turbines are a little more efficient because they run in a circular fashion as opposed to up and down. Okay, so they can be a bit more efficient. All right, so here would be an example of an efficiency problem. Okay, so I have a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work. Okay? While doing only 8.0 times 10 to the 3 joules of useful work. So in other words, the useful work is moving the load from the ground to the third floor, or second floor, sorry. Okay? That's the useful work. We changed the potential energy of the load by 8,000 joules. But the crane used 24,000 joules worth of energy to do that. Okay? How can I tell which one's which? Like, I just kind of told you which one was which, because how did I figure out which one was which?
Your answer will never be over 100, or when you calculate it, it'll never be over that, because once you times it by 100, that would be over.
Right, yeah, I'm never going to get a number when I do this calculation that's greater than 1. Okay? The other thing is that when I looked at this, my useful work, because my answer can never be greater than 1, my useful work can never be the bigger number. Okay? No process is ever 100% efficient, so the smaller of the two energies, if I can't understand the context of the question, is always the useful work. Okay? The smaller number will always be the useful work, the larger number will always be the amount of energy required to do it. Okay? So in this case, what we're looking at is 8,000 joules worth of energy, worth of work done, using 24,000 joules worth of energy to do it. Okay, which gives us an efficiency of 34.8%, which actually isn't all that bad. I know I keep saying that these numbers here that you look at and go, oh, I wouldn't want to get that on the test. Okay, and I'm saying that's actually not all that bad. Okay, what's that? Yeah, I wouldn't want to get 34.8% on the test, but I'm telling you, hey, that's not all that bad. I wouldn't tell you that if you got it on the test. Okay, but in terms of efficiency, it isn't all that bad. Okay, it really isn't in terms of being efficient, converting energy from one form to another. Okay. All right. I want you guys to try some of these problems here. Okay, I don't have the sig digs right on here. I'll have to adjust them. I just haven't done it. Okay, so just give these ones a try. Okay, remember, our formula is this: efficiency equals, okay, output divided by input.
Triangle.
Okay?
You can try to allow us
If you wanted to.